as we transition to more complex and advanced automobiles, the domain of vehicle dynamics and control are going to become very important. Okay. So, to motivate the importance of this particular domain, right, to automotive design, today I am going to take a simple example of anti-lock brake systems, like which all of us are aware of, we might have heard about it, but we are just going to discuss, and then I am going to map how vehicle dynamics and control is applicable to this application. Of course, one could take other applications also and do a similar mapping, so that like we get motivated to learning this field, right, of vehicle dynamics and control, right. So, I am sure all of us would have heard about ABS, right, correct. So, you would have seen if you travel in a car, it is very likely that the car has an ABS, right. So, you would have also seen ABS printed on the rear of the car to show that, demonstrate that that car is fitted with an anti-lock brake system, right. So, it is sort of like today very common in automobiles, mandated by law in certain classes of automobiles, and on the way to becoming mandates in other classes of automobiles on the road today, right. So, if you once again look at the what is a title, there are 3 words: anti-lock, brake, system. So, we sort of understand what a system is. We also understand what brake is, right. For what purpose do we use a brake in a vehicle? No. So, whenever you and I want to sort of like decelerate the vehicle, we apply the brake, and whenever we want to stop it, we continue applying, so that like it comes to a rest, right. That is the broad function of a brake system. Then what does this adjective anti-lock mean, right? Let us first look at that, understand that, then we will come to figuring out how vehicle dynamics and control becomes important. Let us say like I look at only one wheel, even if you take a typical passenger car which has 4 wheels, let us focus on one wheel of the 4 wheels, right. So, if I look at one of the wheels and I draw a simple diagram, let us say without laws of generality, the wheel is rotating counterclockwise at an angular speed of omega subscript w, and let us say the vehicle is moving in this direction. Once again without laws of generality, the vehicle speed is v, okay. So, this is the vehicle speed. So, this is rotating at an angular speed of omega w. If I want to brake, what I do is that like through a brake system, I apply a clockwise torque, right, so that I can start decelerating the wheel, and the deceleration of the wheel results in a deceleration of the vehicle, okay, that is what happens, right. So, this is very evident in a bicycle, most of us drive a bicycle. When you apply the brake, you can see that like the wheel is going to start decelerating, because some brake pads go and contact the wheels, and then like they apply a brake force, right, and a brake torque. So, if we look at what is called as the tire rod interface, so all the forces that get transmitted to the vehicle, let it be for driving the vehicle or braking the vehicle or steering the vehicle and so on, get transmitted through the interaction between the pneumatic tire, right, that we find, and the road interface, right. That is a very important aspect of it. So, if you look at the contact between the tire and the road, like there is a normal force Fz which acts at the contact, because let us say you park a vehicle, obviously the weight of the vehicle acts on the road applies a reaction, right. So, that is the normal reaction Fz, right, and there is a braking force Fz, right, which essentially tries to decelerate the vehicle, right. So, if the vehicle is moving this direction, I need to apply a decelerating force Fx, right, in this direction, right. So, let us call this Fx, right. So, now let us say like I am having a normal braking process. What happens is that my wheel will rotate, I apply the brake, the wheel will start decelerating, the angular speed will start reducing, and the vehicle speed v will also start reducing, and at some time the vehicle will stop, the wheel will also stop rotating. That is normal braking, what you and I desire. But imagine sometimes like we would have seen, right. So, we travel very fast, let us say on a wet road, let us say it rains, and due to some reason I slam the brake. What happens? The wheel may stop rotating, right, but the vehicle is still moving. So, what we colloquially call as skidding, right, we say that, oh, the vehicle is skidding, right, or the tire or the wheel is skidding, right. So, that is when a wheel is said to be locked. So, a wheel is said to be locked if it stops rotating. that is omega w becomes almost 0, but this vehicle speed is still non-zero. Ideally we want the vehicle speed also to become 0 along with omega w becoming 0, but due to some whatever reason, if that does not happen, we are tending to lock, right. So, that is something which is undesirable, okay. And as the name indicates, now that we have understood what lock is, an anti-lock brake system prevents it, right. So, now I hope it is clear what is anti-lock, right. And ABS essentially ensures that it acts along with the existing brake system to prevent this wheel lock phenomenon, okay. So, wheel lock is not desirable. Why is it not desirable? Like what effects come about if we lock the wheel? Of course, one learns deeper when we go in depth into the domain of vehicle dynamics. But let me explain with a very simple analogy why wheel lock is not desirable by using a very simple mapping once again, right. Let us say I am talking with you and I am walking on this floor, right. Let us say the floor is dry. Okay. So, what am I doing? I am placing my feet on the floor, I am applying some load due to my body weight, right. So, there is a normal reaction. Then at the interface between my feet and the ground, I am applying a force which helps me propel myself, right, similar to what we are doing in a vehicle, right. So, that is how I keep on moving, okay. Now, imagine let us say I am talking to you, so I am not focusing on what is there, right, on the floor, but let us say there is a patch of water, right, a puddle of water on the floor, right. So, what am I doing? I am generating this force, like at the interface between my foot and the ground using my what to say bones, muscles and other joints, right. I am generating a force, right. So, now let us say I step on the puddle with the same intensity. What do you think will happen? I will slip, right. Why? My body is still the same, my muscles, joints are still the same. So, in a sense my system is still the same, right, if I look at myself as a system, right. So, my system is still generating the same force, but what has now changed? The capacity at the interface between my foot and the ground has changed, right. So, what is happening is that the interface between my foot and the ground is not able to sustain what I am commanding through my system, that is why I slip. Same story at the tire road interface also, okay. So, that is where a parameter called as friction or traction coefficient becomes important. Some also call this as adhesion coefficient, okay. A commonly used symbol is mu, okay. This is defined as the ratio between this Fx, which is the force acting along the direction of motion or opposite in this case, which is a braking force, what is called as a longitudinal direction. In vehicle dynamics, longitudinal direction means the direction along the motion of the vehicle, okay. So, Fx is the longitudinal force, x denotes the longitudinal axis and Fz is a normal load. So, this mu is defined as a ratio of Fx and Fz. Now, we want this to be as large as possible, so that like I can drive my vehicle or brake my vehicle very efficiently, but that is not the case in real life, right. So, it depends on lot of things, right. One of the important parameters on which this depends is what is called as a wheel slip ratio. See, even when we walk, if I step on the puddle of water, what do I say colloquially? Oh, I slipped, right. So, similarly a tire also slips, right. How do we quantify that? The way we quantify it is that like we take the difference between this vehicle speed V. If I have a purely rolling wheel, right, what we would have studied in even like middle school physics, right, I have a cylinder or a disc rolling on a surface, right, the circumferential speed is r times omega, right. So, Rw times omega W is the circumferential speed of the wheel. So, if I stand at any point on the circumference, that is the speed I will perceive. So, if I have a purely rolling wheel, V should be equal to R times omega, right, of the wheel, but that is not the case in real life. So, there is a difference between the two. So, that is what we capture in the numerator of this parameter. The denominator is the wheel speed, the vehicle speed itself, right. So, this is what is called as a wheel slip ratio, okay. So, the wheel slip ratio quantifies the difference between the vehicle speed and the circumferential wheel speed to the vehicle speed itself. Okay. So, these two parameters become very important for understanding anti-lock brake systems, right. So, if you look at lambda, how it varies, like this formula is typically used for during braking. Okay. So, if we look at this parameter lambda and see how it varies in practice, let us say I have a purely rolling wheel, right. So, V equals R omega. So, what happens to the numerator? Becomes 0. So, 0 means purely rolling wheel. Let us say I have a locked wheel, skidding wheel, right. Omega has become 0, but V is still non-zero. So, what will happen to this ratio? It will become 1. Why? Because this term will go away, I will have V by V, I will get 1. So, you can immediately see that I will have the wheel slip ratio varying between 0 and 1 during braking, correct. So, now if we look at a typical pneumatic tire which are used in road vehicles and we look at their characteristics and we draw what is called as a mu-lambda curve, this is what is called as a mu-lambda curve, right. So, mu, the friction coefficient is plotted on the ordinate, lambda, the wheel slip ratio is plotted on the abscissa, okay, horizontal axis. So, if you typically look at it, like it starts increasing, it peaks around a wheel slip ratio, let us call it lambda p, right, the corresponding mu values, let us say some mu peak, right, and then after that it starts decreasing, okay, and this region is an unstable region, okay. You and I do not want to go here, right, because the wheel is going to tend towards locking, right, and when a wheel locks, it is going to result in certain undesirable effects as far as the vehicle is concerned, okay. So, you and I do not want to go there, okay. So, that is why we either want to operate in this region, that is where we operate most of the times. Let us say you and I drive a vehicle, we do mild braking, gentle braking, right. By and large we are going to operate in this region, right. But however, let us say there is an emergency, let us say there is rain and we are driving on the highway at high speeds, right, and let us say we see some obstacle or some other vehicle in front, like parked or like coming to a sudden stop, what you and I will do is that we will slam the brake, right. Then that may be 1 in a million case, but still that is important for your safety and my safety, right, and that is when we can, there is a risk that we go into this unstable region, and that is where ABS should come into action. So, what the ABS does is that like it does not intervene when we are in the stable region, right, between 0 and lambda p, it lets the brake system do its job, okay. Only when let us say we go to a panic braking maneuver or even a mild braking maneuver or let us say on an icy surface, imagine a road which is covered with ice, right, even if you press the brake a little bit, there is a chance that the wheel may lock because the capacity at the tire road interface is not very high on an icy surface. Then like ABS will intervene and try to ensure that wheel lock is prevented, okay, and that under that scenario we remain as close to the peak value is concerned, right. So, that is the concept behind ABS, okay. So, what we have done till now is that like we have answered 2 questions, right, what is ABS, why one should use ABS, right. Now comes the question how, okay. How does it monitor, how does it keep it near this, right. So, in ABS, if I want to control, if there is a scenario where let us say ABS is triggered, as we discussed, ABS does not get triggered all the time, it gets triggered only under emergency conditions where I have a risk of locking, right, or the wheel goes to a tendency towards lock, right. So, only when I cross a certain threshold lambda it should get triggered. Now, the question is that what is the threshold at which I should trigger the ABS, right, and what is this lambda around which I should control, okay. So, the core concept behind ABS now, as we can see, I want to regulate or control this wheel slip ratio around this lambda p, right, what we have called as lambda p, right. So, that is what is called wheel slip regulation. So, wheel slip regulation is a very fundamental problem in many automotive active safety systems, right. So, wheel slip regulation means I want to control lambda, but there are two questions now, right. Who gives me what is the value of lambda around which I need to control, correct. In the room temperature example, I told that, oh, hey look, I want the temperature to be 24 degrees Celsius. So, similarly, what is this lambda? I know that it is between 0 and 1, should it be 0.2, 0.15 or 0.1, 0.05, who gives me that value? That is question number 1. Okay. Let us say somebody gives me that value, let us say someone says, hey, control lambda around 0.15. Okay, I know this reference, what we call as a reference value, right. But then how do I know what is the value of lambda at each and every instant of time? See, in our room air conditioner, room temperature control example, we figure out that there is a sensor which will measure the temperature in the room and then gives it as a feedback, right, to control. But in real automobiles, right, in ABS, right, someone should give me what is the lambda at this instant of time, so that I can control it. How does one get it? So, typically what happens is that, like, we have what are called wheel speed sensors which will monitor the wheel speed, but then we do not get vehicle speed to the fidelity that you and I want for ABS application. So, someone has to do estimation of this lambda and give us that estimate. Okay. So, we can observe that, like, we keep on breaking down this question of how into multiple problems, right. Two important problems is that someone should tell me what this reference value should be, right, what value should I control it, because on a dry surface this may be 0.2, on an icy surface it may be 0.05, because the mu lambda curve is going to be different for different road surfaces, right. So, you and I can see the road and tell, oh, it is a dry surface, wet surface, or a snowy or an icy surface, right. How does the vehicle figure out automatically, right, when it is running continuously? See, suppose let us say I am driving the vehicle on road today, initially there is a dry surface and suddenly it rains, there is a transition from a dry to rain surface, right. You and I can perceive. How does an automated system which is installed in a vehicle perceive it, perceive that change, right. That is an important question for us to answer. So, someone should tell me the reference value which changes depending on the condition, and someone should also tell me what is the actual value by giving an estimate of it, then only I control. And the way we control is by using the brake system. Okay. So, we have brakes on the vehicles, like if you take a look at bicycles and typical motorcycles, we have mechanical brakes, right, it is very visible to us. In cars, light commercial vehicles and all, we have what are called hydraulic brake systems, like you press a brake pedal, there are some hydraulics which apply the brake. In trucks, buses and all, there is a pneumatic brake system, like it uses compressed air for braking, right. So, someone should regulate that braking to ensure that this wheel slip is kept around the same limit. So, we can observe that there are so many technical questions one can pose, right. We have identified a few, and in order to solve them we need a good understanding of the fundamentals of vehicle dynamics and controls. So, only if you understand the fundamentals of vehicle dynamics, we will be able to figure out how the vehicle will behave when I control using an ABS and what corrective action to take. And once I determine what corrective action to take to ensure that the wheel does not lock, I need ideas from control systems, right, to essentially ensure that that corrective action is actually implemented. So, we need a good understanding of the science of vehicle dynamics, a science of vehicle control systems, in addition to other things. We also need good practical hands-on knowledge of how sensors, actuators and all work. How do I program into an electronic control unit, how do I essentially process signals, like, so you can see that this is a multi-domain system, right. It is quite challenging, quite interesting, right, but to design it one needs fundamental ideas from this domain. Okay. That is why vehicle dynamics and control is important. Okay. So, we have taken a simple example to understand it, and today we are transitioning to electric vehicles, and of course ABS is there on electric vehicles also, right. So, the questions become further what to say, enhanced in the scope. What do I mean by that? So, typically in an electric vehicle, we would have realized it, right, or we would have read about it, that there can be something called regenerative braking. If you buy even an electric two-wheeler or an electric car today, you know, like we would read that, okay, some part of the energy during braking is recuperated and stored in the battery for future use, right. That is what is called regenerative braking, right. In a typical vehicle, road vehicle, we have what is called friction braking, right. So, that is during braking, you know, like we have disc brake or drum brake and some friction material in them, and that essentially you know, produces friction, and that produces the braking force. But during that process, the kinetic energy of the wheel and the vehicle is converted into thermal energy or heat energy, and that is why if you will feel that, oh, brakes are hot after a long drive, right, and frequent braking. So, that is friction braking, but in electric vehicles some component of braking you can get through regenerative braking. So, you save energy, you recuperate some kinetic energy and store it in the battery, right. Now, the question becomes, you know, like if I have regenerative braking, how do I implement ABS in that, okay, because in conventional vehicle we use pure friction braking to get ABS action, but in an electric vehicle, let us say I have to design an ABS for an electric car tomorrow, right. I need to ensure that I control both my traditional friction braking and also regenerative braking to get a good mix of braking effort, right. So, we can see that there are all, what to say, additional questions which are posed as part of the scope of design. So, once again we need to know how to control the motor, right, how to essentially understand the dynamic response of an electric vehicle and so on, right, in addition to all the questions that we have already posed. So, one can observe that the domain of vehicle dynamics and control is important, okay, to understanding the dynamics of any road vehicle, let it be a vehicle which is driven by an internal combustion engine or a vehicle which is driven by an electric motor, an electric vehicle, or even a hybrid vehicle, right. So, it is important for us to know about it. Of course, this is one of the domains, right, which one needs to understand to become a well rounded automotive design.